Hello, guys. Welcome to the final lecture as far as actual topics go for the Calc 1 class. I just wanted to say thank you for a good year. I know things got weird around quarantine. Um, I'm proud of you guys for sticking through it. Um, Please excuse the cheesy GIF that I have. I think I'm way cooler than I actually am. Also, fun fact, it's GIF and not GIF because the G stands for graphic, which has a hard G sound. Anyway, that's what'll happen if you Google things too much. Let's dive into it. Get this over with. We are on section 5.4, and it is called Working with Integrals. Okay, so first of all, we're going to talk about integrals of even and odd functions. So I don't remember how much you guys recall, or I don't know how much you guys remember about even and odd functions. You probably learned it in either pre-calc or maybe trigonometry or college algebra. I'm not sure. I haven't taken those classes since probably before you guys were teenagers, so it's been a bit. Anyway, we'll talk about our two categories, even and odd. So, if you guys remember the technical definition of an even and odd function, an even function is if the function values f of x are equal to the function values for a negative x. So, if you flip across the y-axis, there's symmetry. So, y-axis symmetry. Some examples include the function, the absolute value of x, that's even. Another example is x squared. And another example is cosine of x, which looks something like this. Right, so if we flip across the y-axis, these are the same, so we have y-axis symmetry. And what it's saying up here with the f of x equals negative x, f of negative x, is the values for our function on the right-hand side are the same as the values for our function on that respective left-hand side. So if we go over, say, 2, that's going to have the same value as if we go negative 2. Okay? And then odd functions are where f of x is equal to negative f of negative x. And also it's important to note that not every function is even or odd. You don't have to be one or the other like numbers do. You can be neither even nor odd. Okay? We'll do an example of that later. So this is called origin symmetry, which is kind of like if it flips diagonally. So some examples are x cubed and sine of x, which looks like this. Technically just the line x is odd. So if we look here, this is being flipped over the origin. So this, if we flipped it, is what this is. This is just this flipped over the origin, right? So our line of symmetry would be like this, but it's kind of like flipped through that, right? So it's not exactly symmetry across that line, it's origin symmetry. So it's like a symmetry across that line and then a flipped upside down. Okay, and what it's saying with the f of x is equal to negative f of negative x is our values that we get, say, on this side. So say this is 1, 1, because 1 gives us a positive 1. If we have a negative 1 for x value, it's going to give us a negative 1 for f of x value. So it's just saying that when you plug in a negative number, you get a negative version of what you'd get for plugging in a positive number. Example of something that's neither even nor odd is, say, g of x equaling x cubed plus 2. So we know that x cubed itself is odd. But if we move this function up 2, which would look like this-ish, we can see that that no longer has that origin symmetry. Now we've got this extra bit above the origin that's going to make it non-symmetrical. And so that guy doesn't work. There are some cool properties involving the integral of these functions. And so I'm going to write them out first and then explain why they are the way that they are. So if a function, and you never have to use these rules, they just make it easier to calculate things. So it's just like a nifty trick to make your life easier, which is my favorite kind of trick. So if f of x is even, then the integral from some number a, negative a, to that same number but positive of f of x dx is equal to 2 times the integral from 0 to that number of f of x dx. So let's go look at what's happening with our even functions. So if we look up here, that's saying that, let's do this in yellow. The integral of the whole thing from negative a to positive a is equal to the same thing as the integral of the positive a times 2. Which should make sense, right? Because this area over here is the exact same. So we can just calculate this guy and multiply it by 2 to account for both of them. And the reason that's helpful is because plugging in a 0 is usually a lot easier than plugging in this negative a value. So then you only have to deal with one non-zero value instead of 2. All right, let's look at this second rule, which is for odd functions. So if f of x is odd, then the integral from negative a to a of our function is actually just equal to 0, which is even cooler. So if we look up at our odd functions, there we go. So that's saying the integral from a negative a to a positive a. Again, a is just an arbitrary bound, but we're going from the same number negative to the same number. These guys have to match. And it's saying that this area is 0, which should make sense because this area is the negative version of this area, and a negative, let's say any number c plus a positive, that same number c, negative c plus c is 0, right? So these cancel each other out. So that's just kind of some nifty tricks. We're going to do one example, I guess. Yep. An example. So the integral from -2 to 2 of x to the fourth plus 3x to the third dx. So we know that we can break this up into two integrals, -2 to 2 of x to the fourth plus the integral from -2 to 2 of, we bring the 3 out front, 3x cubed dx. And so we're thinking about even and odd because that's what we just talked about. And we know that this is an even function and this is an odd function. So this guy actually just goes to 0, which is nice. So we only have to focus on this even function, which from our rules we just established, we can evaluate from 0 to 2 instead of -2 to 2 as long as we multiply it by 2, because we're just doubling that area to account for the negative portion. So 0 to 2 of x to the fourth dx. Again, our second integral became 0, so we don't really have to worry about it anymore. We're going to get 2 times, when we take this integral, we get x to the fifth over 5 from 0 to 2, which gives us 2 times, in big parentheses, 2 to the fifth over 5 minus 0 to the fifth over 5. And this is why finding the area from 0 to 2 instead of -2 to 2 is nice, because this entire portion goes to 0, because 0 divided by a number is just 0, and we get 2 to the sixth over 5, which is 64 over 5. 2 to the fifth becomes 2 to the sixth because we're multiplying by this 2 on the outside. Okay, so I know that was quick, but you guys know you can pause these videos or decrease the speed, and that's just a handy trick using even and odd functions. Our last thing that we're going to talk about is average value of a function. Okay, so if you remember when we were talking about derivatives, we compared it a lot to like instantaneous slope versus average slope. And we talked about how like the mean value theorem for a derivative was saying that if a function is continuous, at some point along that function, we're going to hit an instantaneous slope that is the same as the average slope. And the same thing is true for integrals, but we need to define how to use an integral to find the average value of a function. That was a kind of a convoluted introduction, but don't worry about it if you didn't understand what I said. It was mostly for my own benefit. Anyway, so if we have some function, let f of x be integrable, aka you can take the integral on a to b then the average value of the function f of x on a to b is, we write this as f of x bar. That's what we call the line on top of f of x, and it just means average or mean value if you took statistics. And it is equal to 1 over the right-hand bound minus the left-hand bound times the integral from a to b of our function. Okay, so that's the average value of our function. And if we look at like a picture of this, we have our axis, x, f of x. If we have some function, ooh, I don't want to deal with that. Let's do something like this. Then at some point along this function, there's an average value, as if we were to add up each of these individual values of f and find the average of all of them, it's going to be somewhere like here, I'm guessing. Then that's what this is representing, is that average value of f. It's, again, this is one of those things that it's not like super important that you understand it at this stage. It's just something that we want to introduce. And it's a good way to practice using integrals, is having this application and then saying, find the average value of a function, which basically means find the integral divided by 1 over the top bound minus the bottom bound. One cool thing to note is that we talked about the mean value theorem for derivatives. We called it the MVT. And it's also true for integrals. And it basically says that if f of x is integrable on a to b, then f of x achieves its average value on a to b. So that's saying if this function, if you can take this integral, you will find that average value at some point in the interval. So it's just saying that it does exist within the interval. Again, not incredibly important, but we're going to do an example just because, and then we're done. This is our last example. It's going to be find the average value of the function f of x equals 3x squared plus x plus 2 on the interval 2 to 5. So using our formula, the average value of f of x is going to be 1 over our top bound minus our bottom bound, so 5 minus 2 times the integral from 2 to 5 of our function, and that is 1 over 3 times 3x cubed over 3 plus x squared over 2 plus 2x. If you can't keep up with this integration here, you should probably go practice section 5.3 in the online homework just to get more familiar with calculating definite integrals. So that's a good hint. And we're evaluating it from 2 to 5. And we get 1 over 3 times, oh, I'm going to need more space in this, hold on. 1 over 3 times 3 times 5 cubed over 3 plus 5 squared over 2 plus 2 times 5 minus, I'm going to distribute this 1/3 now so I don't have to have a bazillion parentheses. So I'm putting a 1/3 here and a 1/3 here. And it's going to be 1/3 times 3 times 2 cubed over 3 plus 2 squared over 2 plus 2 times 2, which is the same as 2 squared. We're going to have 1/3 times, our 3's cancel, we get 125 from 5 cubed plus 25 over 2 plus 10 minus 1/3 times, our 3's cancel again, we have 2 to the 3rd, which is 8, plus 2 squared over 2 is 2, plus 2 squared is 4. Honestly, at this point up here, you could have plugged it into Symbolab. At this point here, you can plug it into Symbolab. I would highly suggest it. I could do all of this, but I'm going to skip some steps because I am not in the mood. We have 1/3 times 295 over 2 minus 14 thirds, which gives us 295 sixths minus 28 sixths, sixths plural, equals 200 and, can I do mental math? We shall see, 67 over 6. Alright. That is actually simplifiable, but I'm not going to do it. Anyway, that is the end of calculus. So thank you for making it this far. I will be posting a final exam review video next week. I highly suggest you watch it. Please do the online homeworks for the sections you aren't comfortable with. This is all brand new material, and remember, 11 out of the 16 questions are going to be on on sections 4.9, 5.1, 5.2, 5.3, and 5.4, which we just covered. So please make sure to do at least some of the online homework for those sections. Yeah, that's all I have to say.